Welcome back, my friends, to the show that never ends. We're so glad you could attend. Come inside, come inside. There behind the glass stands a real blade of grass. Be careful as you pass. Move along, move along.
Hi, and welcome to MetalForming Live, where the pages of MetalForming magazine come to life via a three-part online educational event. I'm Brad Kuvan, Editorial Director of MetalForming magazine at the Precision MetalForming Association. And along with PMA President David Klotz, MetalForming publisher Mike Voland, our senior editor Lou Kren, and the rest of the PMA and MetalForming magazine team, it is my distinct pleasure to welcome you to this one-of-a-kind event. For 3 consecutive Wednesdays in July, tune in as Lou and I host panel discussions with MetalForming magazine's 3 expert columnists, Pete Ulentz, Danny Scheffler, and Aaron Bellur, along with special guest panelists, each experts in the field. These 90-minute roundtable discussions will address 3 topics of critical importance to metal formers: how newer materials such as advanced steels and aluminum grades impact metal formers, simulation of progressive die designs, and optimizing press stroke rate without investing a lot of money. Each of these sessions will feature a brief technical presentation by one of our columnists, followed by lively discussion by our panel, and of course the panel will address your questions. So please, we invite you to participate and ask questions of our panelists. I want to thank all of you for attending today's session, and of course thank our sponsors as well. We look forward to seeing you at our remaining sessions as well.
Delmia Works runs this company that allows you to analyze where you are, see where you're going, and figure out what the path is that's going to get you there. Every step of the way through your production process is driving into the balance sheet and the profit and loss.
Delmia Works has helped us provide all the team members here, all the individuals within the business, with the best tools to give them the best chance to do the best job they can.
Hi everyone, thanks so much for the opportunity to be here today. My name is Michael Hart. I'm a Senior Director of Product Management with Plex Systems. Plex is proud to sponsor the 3-part series of MetalForming Live. As the metal forming industry continues to evolve, metal stampers and fabricators like you must think outside the box to overcome new challenges and hurdles. Technology solutions, like the ones being discussed during MetalForming Live, are essential to maintaining productive and high-quality operations. In addition to these technologies, Plex Systems' smart manufacturing platform continues to evolve alongside metal formers and fabricators. Plex was born on the platform and purpose-built to deliver the total visibility and integrated quality metal formers and fabricators need to support efficient operations, increased throughput, compliance, and cost control. We recognize that manufacturers need to adopt technology in different ways, which is why we recently announced the modularization of the Smart Manufacturing Platform. This approach allows manufacturers like you to build a smart manufacturing technology strategy that focuses on flexibility, quick implementation, and ease of entry into Industry 4.0. We here at Plex hope you enjoyed these live events from MetalForming Magazine and the PMA. And we're proud to be supporting the event. Enjoy.
Alrighty, here we go. For one final time, MetalForming magazine is once again live, this time for the 3rd and final installment of our 3 online events. And today we're covering optimizing press stroke without investing a lot of money. This time you'll notice that we have a little different format with everyone in their separate Zoom boxes rather than all of us being together. But as usual, I'm joined again here today by our senior editor, Lou Kren, and our distinguished panel of magazine columnists and special guests, everyone experts in their field. Before we launch into the presentation and panel discussions, I again want to thank the sponsors of these 3 events, whose generous support makes them all possible. Delmia Works and Plex Systems, both of whose welcome messages you just saw, as well as Nidec Press and Automation, Pacific Press Technologies, Principal Financial Services, and of course, PMA. And here from PMA with a brief welcome message for us is our Vice President of Sales and our magazine publisher, Mike Voland. Mike, go ahead, take it away. No, you're muted. Go ahead. Mike, you're muted. Mike, yep, there you go.
PMA's Vice President of Sales and the publisher of MetalForming magazine. My apologies for being late on the draw with that. I am pleased to welcome you to our final session of MetalForming Live. This has been a great 3 weeks with MetalForming Live, and I hope you have enjoyed the content as well as the platform. Just a few more words about our association before today's session begins. PMA is the full-service trade association representing the $137 billion metal forming industry of North America. Our more than 900 member companies are primarily contract manufacturers using metal stamping, precision sheet metal fabricating, roll forming, slide forming, metal spinning, and related assembly and finishing technologies, along with the suppliers of equipment, materials, and services to the industry. PMA provides many benefits and services, including networking and industry benchmarking, advocacy at the federal level, and numerous opportunities for management and technical education. In addition to these services and benefits, PMA also has a robust educational foundation, which is focusing on the workforce of tomorrow. If you would like more information on becoming a member company, please visit our website, pma.org, or you can certainly reach out to me directly, mvoland@pma.org. With that, I will turn it back over to Brad. Thank you all very much and have a great session.
Terrific. Thanks a lot, Mike. So we're just about ready to get started. Just a reminder that today's meeting is being recorded for archiving, as were the other two sessions, and the recorded event will be posted to our website within the next few days. So we'll let you know via email, as we've done in the past, when that recorded session is available for viewing online. It'll be most likely tomorrow sometime. Also, all of you in the meeting are in listen-only mode. So that means that other listeners will not be able to hear any audio from your site during the program. However, you can communicate with us by submitting any questions or comments using that question box, which is located on the control panel of your Zoom screen. And then you'll use that same question panel rather than the chat panel. Use that question panel if you want to pose questions to our panelists throughout the meeting, which we really encourage you to do. We want these to be interactive sessions. We want your participation. We've had a lot of questions from the previous two sessions, so let's make this one equally interactive. So without further ado, it is our pleasure then to welcome our panelists. We're going to ask them each to introduce themselves briefly before we go ahead and launch into the presentation. So Pete, you want to go ahead first and introduce yourself, please?
Sure. Hello, everybody. My name is Peter Eulens. I am the technical director at Precision Metal Forming Association. I worked in the metal stamping and tool and die industry for 38 years before joining PMA in 2015. And I've also been fortunate enough to write the monthly column, Tooling by Design, for Metal Forming magazine for the past 16 years.
Thanks, Pete. Danny, how about you?
Hello, everybody. My name is Danny Schaeffler. I write the Metal Matters monthly column for Metal Forming magazine. I'm also president of Engineering Quality Solutions, a consulting firm specializing in sheet metal forming and sheet metal formability from a materials perspective.
Thanks, Danny. And Aaron, how about you?
Hello, everyone. This is Eren Bildur. I have a bi-monthly column called Cutting Edge in MetalForming magazine since 2020, only 2 years old. And I also am president of two different companies. One is called Bildur MetalForm, where we do engineering services and consulting and training, and Bildur Makine, where we do press refurbishing and automation. I'm looking forward for today's discussion. Thank you.
Thanks, Aaron. And then last but not least, David Diaz Infante.
Hello, everyone. My name is David Diaz. I'm the civil press scientist for Nidec Press and Automation. And here at Nidec, my job is to help our customers to better use their servo presses from two perspectives. One is increasing production rate, and the other is from mobility perspective. So.
Excellent. Thanks, David. So now we'll go ahead and we'll turn things over to our presenters today, which is Pete and then David. So go ahead, guys.
Okay. Thank you, Brad. Appreciate the introduction, and welcome everyone to this third edition of MetalForming Live. Today, we're going to talk about optimizing press stroke rate, or strokes per minute, in your press shop. And we're going to try to approach this from the standpoint of what can we do to improve productivity without investing a lot of money. And so for the most part, that's going to involve simply just doing things right. So let's start off with, what is the impact of 1 stroke per minute? You know, in a lot of organizations, unless we're going to make a significant impact on productivity, we kind of don't look at these small incremental steps. But let's consider for a moment the impact of just getting 1 stroke per minute out of all of our processes. What does that mean for us? Well, basically, it'd be 60 parts per hour, or 480 parts per day. That's a little over 115,000 parts per year, based on working an 8-hour shift and 240 days per week. Even if you're working 2 shifts, and even at 90% efficiency, that well exceeds 200,000 parts per year. Now, let's assume that you make 8 cents per hit as an average. That 200,000 plus parts per year would equate to a little over $16,000. Now, consider, how many presses do you have? You know, a medium-sized stamping plant with maybe 30 presses. That's nearly $500,000 per year, just by getting 1 stroke per minute out of each die that we run. So we're not looking at making huge, dramatic improvements. We're looking at just getting 1 stroke. So how easy is that? Well, it can be very challenging. And that's probably the primary reason that we don't do it as frequently. Because in metal stamping processes, we've got a lot of variabilities to deal with, and we have to control those variables. So much like this padlock that we're looking at, this padlock has 4 tumblers. Each tumbler has a number from 0 to 9. So we got 10 different possibilities for alignment in terms of a numerical value that we may come up with on the tumbler. And we have 4 tumblers. That means there's 10,000 different combinations possible with this lock. But as we all know, with a padlock, there's only 1 combination that'll open the lock. Now, some of us have processes that only have a few combinations of very important process variables that will unlock our process and where we get successful results. And you'll know the processes that have these very few variable combinations that give us the results that we're looking for. Typically, the results will be a part to print and a part that the customer will accept. These processes that we struggle with are the ones that take 45 minutes to set up and then 2.5 shifts to get a good part that quality will accept, that we can ship to our customer. And then we struggle at every coil change. So every coil change brings another set of variables. And so we've got these very few combinations that give us the results that we're looking for. Now, if we take these variables and just look at them in terms of process parameters, for example, setup accuracy, can we think of 10 things in our setup that relate to accuracy that can vary, that can give us different results? You know, is the die aligned properly? Is the pilot release set accordingly? Do we have the right feed height? Straightening, do we have this, is the straightener set properly? Is it maintained properly? Do we have bent rolls that's causing issues for us? What about equipment maintenance? You could probably think of 10 things in your equipment that can cause variability. For example, not using the counterbalance, not setting the counterbalance pressure properly, not maintaining the give clearance and doing our press maintenance or our tool maintenance. And die protection creates issues for us. A lot of times I hear people say that they disconnect their die protection because they have nuisance faults. Well, if we're getting a fault, it's kind of telling us what we're looking for. The nuisance is trying to figure out what are the variables that are tripping that. And so, you know, just these four things can create 10,000 different variable combinations. And I haven't even addressed materials. Danny spoke 2 weeks ago on materials and the different variables that we can see in materials and how we buy it, how we receive it, what we understand about it. And then if you add documentation into this, a lot of companies don't document what these process variables are and how to control them very well. So you could have 100,000 to 1 million different combinations that are variables that affect our stamping process. Now, fortunately for a lot of processes, there are thousands of combinations of these variables that result in success. But in other processes, not so many, maybe only a few hundred. So we have to know what those are and be able to control those. Not understanding and communicating accurately or documenting the variable parameters that give us the best outcome is usually the root cause for our inconsistency, because we haven't identified, documented, and controlled these variables. Yes, it's true that, you know, most of us have setup sheets, such as the example here. Well, we'll have important information in terms of perhaps how to align the dies or quick die locators, how to properly set the shut height, what the tonnage should be, roll pressure, lubrication. All of that is true, but they're numbers on a piece of paper, or today in some of our press controls, we can enter this and pull that up as a recipe for a production job. But how do we know what we selected and inputted is correct? If we're doing something wrong or it's not optimized, when we document it or put it into a program in our press controls, if we've built in inefficiencies, we are pretty much going to replicate that inefficiency for the entire life of that product that we're running. I want to cover a couple important factors that I see as impacting progressive die performance. We'll talk about progressive die performance, talk a little bit about transfers as well. But for progressive die components, I'd like to talk about some things that I believe are important. The first is establishing the proper pass line or feed line. What should that be? You talk to a lot of people, like a lot of things in our industry, we get a lot of different responses, and the responses that we get can be appropriate for many different situations. But in general, I would say that our pass line should be adjusted and verified with each setup so that the feed, that the material coming from the feed introduces the material exactly parallel with the height of the lifters in our die. So if we've got a die that has any lift where we're lifting the strip, I suggest that the raised position of our lifters is what the feed line should be. And this kind of makes sense because we want no obstruction in our feed. If we have our feed units set lower, we're feeding uphill and then we're changing direction to continue feeding into the die. So this change in direction is what's going to give us problems. Now for dies that have little or no lift, such as a lot of high-speed applications, what we would be looking at is we want to make sure the die surface and any feed bridge or extension that we have are all on the same surface. And a lot of times in high-speed applications, to set the feed line, what we'll do is we'll actually get in there with an indicator indicate the die surface, indicate the feed bridge. If there's a feed shelf coming off from the feeder, what is that height? All of this should all be in line, because especially for very thin materials running at high speeds, any change of direction is going to pose an opportunity for the material to bend, buckle. We're going to have short feeds, missed feeds, things of that nature. So in my opinion, this is very important. So if this is very important, we have to have a mechanism or a way to set it properly. So our machines should have some type of a scale mounted to them so we can make adjustments to the pass line. So here on the left is just a feed unit that's independent, that sits on the floor. It's mounted to the press structure here to the right. Right here, you can see where the adjustment is made. We put a crank in there and we can crank the unit up or down. Now, this particular customer took a scale, epoxied the scale to the side of the machine and made a little pointer. So if the setup required that the feed be raised 10 millimeters or lowered 8 millimeters, they can get an exact measurement off of the scale and have much more accurate settings. On the right here, we see there's a scale mounting here. Some of the press manufacturers include that with their press. And so we can see how it works in this application with the Bruderer press. The other thing that I suggest is that now that we've got the feed in at the height that we want, we kind of want to maintain that. So I recommend that we use some type of coil bridge to support the die strip in between the feed. Okay, here you can see in the center, here's the feed unit, here's the die entry. We've got quite a distance here from the feed exit to the entry side of the die. So we need to support that material. And we need to support that material in some type of, for lack of a better term, professional way. I cannot tell you how many times I've seen stacks of wooden pallets or plastic parts containers that are turned upside down to support the stock strip. Think about your stamping operation. You got a multi-million-dollar press line with a die in there that probably costs more than most of our homes. And we take a $15 worth of pallets and throw it underneath the material to help keep it level in the die. It just doesn't make sense. So use or make some type of a coil bridge. Okay. One of the important things here is to notice is that these coil bridges generally have rollers on them. So we want to minimize the amount of friction, because when we're feeding, friction is going to be our enemy essentially. Right? We want a smooth feeding without any resistance. So if we're feeding across wooden pallets or other types of containers that are turned upside down, that's one of our variables that we can't control. What is the friction there? Is that causing our feed rolls to slip? Is it causing a late signal for the material to reach the end of the die, for the signal to go to the press controller to say whether or not the feed made its pitch or not before cycling through the next operation? So very important. The other thing that's important is the feed angle. Okay, so when we talk about feed angle, what is the feed angle? In a nutshell, it's the amount of time that we have to feed the material from the time that the press opened, okay, the die opened, the pilots have pulled out of the strip, parts have fallen out of the die, they're clear, cams are back. This is what we refer to as a clear path. Sometimes mistakes are made. We're looking just when the pilot disengages to begin our feed, but what we have to also consider are our cams back, have parts ejected properly. This clear path may entail more than making sure the pilots are out of the strip. And then we want to feed the material. On older feeds, back in the day, typically we fed from 270 degrees to 90 degrees. It was relatively fixed. there wasn't much that we could do to alter it. With our mechanical feeds, with the air feeds, we were able to put relays on them, rotary relay switches, and maybe we would be able to expand the feed angle from maybe 250 degrees to 120 degrees. So we were able to increase this feed angle, which is important. The larger this feed angle is, the more time we have to feed. The more time we have to feed, that means we can move the material slower to make sure it doesn't slip, that the progressions are accurate. But things changed when servo feeds and die protection kind of came into the mix, okay? So now we have sensors to deal with. We have servo press timing to deal with. So it makes all of this timing much, much more complex. So in general, as I said on the previous slide, we'll want to run our feed line as slow as possible, okay? And we want to use as much of the feed window that we have. So we need to determine what our maximum feed window is. For example, how much time do we have here to move our material? And the reason that we want to run as slow as possible is, one, it increases accuracy. Two, we reduce the potential for the rolls to slip, for the feed rolls to slip. If we've got some really rapid acceleration, we can get some slippage. We have better loop stability. We don't have the loop dancing around uncontrollably. That reduces the probability of buckles and die jams. And when we slow down our feeds and slow down our processes, it's this right here that we're usually dealing with. We're going to slow things down because we're getting buckles and die jams. And when I say slow things down, we're going to slow the press down, because the press is tied to the feed. If I slow the press down, I slow down the feed, and these problems go away. But what I'm suggesting is we need a way to maintain press speed, but still find a way to reduce the feed speed. And this is what we're going to be talking about here. So, and it also reduces feed line maintenance costs, because we're not rapidly accelerating and decelerating our materials that we're trying to feed through the dies. So coming back to our angles that we talked about, when it comes to die protection, one of the things that's really important is this concept of a critical angle, okay? We have to know what the critical angle is for our process. And what the critical angle is, it's the last degree of rotation or angle that a fault can be initiated so that the press will stop before it closes on the strip. And this is going to be affected by press speed. It's going to be affected by the slide and die weight, the counterbalance pressure, the condition of the clutch, where in the stroke that the signal is initiated. In the stroke, our slide velocities are not constant. At 270 and 90 degrees of rotation, our slide velocities are actually at their greatest. So they're moving at their maximum speed. It's going to take longer to stop the press, as opposed to if a signal was stopped near the top of the stroke, where the slide is beginning to come to a stop, so it can change direction and then continue to close the die. So this critical angle, how do we determine this? So one way is to inch the press down and observe when the pilot, the tip of the pilot, not the locating body diameter, the tip of the pilot. Once the tip of the pilot is in the material, we can open the feed roll. Because if the strip were to shift one direction or the other, the tip of the pilot is in there to pick up the hole and help position it. If we lift the roll too late, we gauge off of the full diameter of the pilot. If we have an overfeed or an underfeed condition, we're going to distort the hole, and we're not going to have accurate positioning. So this is very important to establish where that die closure is. Where does the tip of the pilot begin to enter the strip? Once we determine that, for this example, we'll use 125 degrees. Our pilot is entering, the tip is in, we're at 125 degrees of crankshaft rotation. At this point, we've established that. We'll open the press, we'll disable the sensors, and we'll back out the material. And then what we're going to do is we're going to run the press at normal operating speed. Now, when I say normal operating speed, the normal operating speed for that specific die, okay? You don't want to run the press at maximum speed or the slowest speed or an average speed. You want to run it at the speed that you're going to use for this particular die. Then we're going to select the brake monitor option from your press control, or if you're using a remote brake monitor, you select that option from the remote brake monitor, and you're going to select the 90-degree brake test. The 90-degree test, if we test at 90 degrees, that's the fastest that the slide is moving. That'll give us a worst case stopping performance. After the press stops, we'll record that angle. In this instance here, we can see the stop angle is 96 degrees. Let's subtract that from the die closure angle, which was 125. The result is 29 degrees. So here's my critical angle, 29 degrees. This critical angle will change with press speed, because the faster the press is going, the longer it's going to take for the press to stop, for the brake to stop the press. Then we want to document that. So here is a sensor window setup sheet, and we've got a number of different sensors here. What type of sensor? Is it a top stop? Is it an e-stop? When does it come on? When does it turn off? And it's also important, in my opinion, to create some details or notes. You know, what are you trying to accomplish here? We're in this short feed, we're using a small window to decrease feed-related incidences. Here on the cam return, we're going to use a small window so the cam does not interfere with the feeding. On material buckle, we'll use the whole sensor window that we have available. Other related events that I think we should include is, what is the critical angle? Okay, and what is the must stop angle for that die? Okay, so now we know what the must stop angle is, we know what the critical angle is. How did we determine it? We used a 90-degree brake test. Document that. Okay, how did we determine what the must stop angle is? We did it by checking the die closure angle. Okay, and then Then in our notes, we want to say it was established for this tool running at what speed? Remember, I said speed will affect the critical angle. 30 strokes per minute in our 600-ton press. Which 600-ton press? Press number 135. Well, we all have, all of our presses, we have 600-ton presses. They're all built by the same manufacturer. What difference does it make? Well, all of them are in different states of maintenance. The brake might be worn on one press compared to another that just had a rebuild. And so one press has a longer stopping time than the other. Also, what was the counterbalance pressure that was used? Changing the counterbalance pressure will affect the stopping angle. So now that we have this, we're going to set the pilot release timing. The feed roll should open, as I said, when the tip of the die, the tip picks up the pilot. If the die has little or no lift, you can close the feed roll or the pilot release, set the pilot release to close at or near the bottom of the press stroke, providing the die has little or no lift. A blanking die, for example, no problem closing it at the bottom of the stroke. What I see a lot of times is, regardless of the die, a lot of press operators, die setter people will set the pilot release to close when we're at the bottom of the stroke. The thinking is that I've got the material constrained, the pressure pad and the stripper are holding it, it's been located, it can't move. This is an opportune time to close the feed rolls. But that's a bad decision if the die has some lift. If the die has lift, the feed roll should lift when the lifters have come to the full up position, or close them at the last possible minute. Why? Let's look at what happens very quickly here. Here's my feed rolls. I'm feeding into the die. I suggested that we should feed into the die at the level of the raised lifter. So here's what we have. The die closes now. It travels this distance of A. So we're going to say that's 4 inches for this example. The die closes. The hypotenuse of this triangle, which we can calculate, is going to be longer. We know from our high school geometry, the hypotenuse of a triangle is the longest side. Well, this side got longer because it pulled material from the feed. If we close at the bottom of the stroke, if I close the feed rolls at the bottom of the stroke, I have this extra material in there. We can calculate this. I'm 36 inches from the feed to the die entry. If I calculate this leg C, it's 36.22. It's almost a 1/4 inch longer. So when this die raises, I've got a 1/4 inch too much material in here. So it may want to buckle or arc a little bit. And as soon as the strippers separate and the pilot comes out, bang, the material moves forward. And what it appears to the operator or the setup person is, I've got a long feed. And they may deal with it by shortening the feed length. So if I have a 12-inch feed, we might reprogram that to be 11 inch and 3/4. And that is the wrong approach. You don't have a feed issue in terms of feed distance. You have an issue here that is pilot release. When we get closer, when the feed gets closer, maybe my issue goes away, or it's less as I get closer to the feed. It's not. When the die and the feed get closer together, what happens is this angle becomes more severe. So in this instance, I'm at 24 inches, but this leg here is 24.331. It's well over a quarter of an inch. It's approaching 3/8 of an inch difference. And then if I have a die that has a shorter lift, and this illustrates why dies with no lift or very little lift can have the pilot release timing set anywhere in the stroke, at the bottom of the stroke. If I have a 1-inch stroke and I close at the bottom at this 24-inch distance, I might be off 20 thousandths of an inch. My piloting, depending on the thickness of material and the types of piloting I have in the die, may be able to correct for that. But when I get into high lifts like this, our piloting is not going to be able to correct for an error like that. So that's one area to look at, and then document it, okay? How was the pilot release set? Tip entry, we mirrored the angle on the upstroke. We took off 5 degrees for the lift and closure due to lag time. And our lag time is based on running 30 strokes per minute. We haven't talked about lag time. What is lag time? In my opinion, this is one reason that setting pilot release timing is so complicated. We have relays, we have air cylinders, we have an air cylinder that's going to lift the feed roll. Well, we have to send a signal to charge a coil to activate a switch. That might take 13 milliseconds. The solenoid might take another 13 milliseconds before it redirects air from one side to the other. And then we need more time to exhaust the air from one side of the cylinder to fill the opposite side. So that can be anywhere between 35 to 45 milliseconds. Most feed manufacturers I've talked to say that they believe the lag time is somewhere around 35 milliseconds. If you're not maintaining your air cylinder on your feed, it leaks a little bit. The reaction time could take a little bit longer. Maybe it's 45 milliseconds. Okay, 45 milliseconds. How could that be important in our operations? I mean, a blink of an eye is like 200 milliseconds. How can this be important? Well, let's look. At 60 strokes per minute, our process is going through 1 stroke every second. And 1 stroke is 360 degrees. A second is 1,000 milliseconds. So if we divide that 1,000 milliseconds by 360 degrees, that means for every 2.8 milliseconds, the press rotates 1 degree. So let's look at the example. We're running 60 strokes per minute. That's 2.8 degrees per millisecond. I got a 35 millisecond delay. that's a roughly 13 degrees. If I got a longer signal delay, it's roughly 16 degrees. Why is that important? Well, if you program the roll to lift at 125 degrees, it may not actually lift until 138 or 141. And we're going to have the same lag time when the rolls close. And this changes with press speed. So if we're going to be looking at increasing strokes per minute, we have to make sure that we're looking at pilot timing. We have to look at what's our sensor window. How did the critical angle change as well? So these are some key points that I wanted to bring up relative to progressive die operations. That's a pretty common process in most manufacturing plants, but there's other areas to look for improvement. So especially if you have a servo press technology, how are you synchronizing the press with the feed timing? With servo presses, you may end up having the program based in distances instead of angles. How do we optimize and couple transfer system motion profiles, implementing anti-vibration strategies, rethinking how we train press operators, what skills are required or desired, and how can we improve uptime through improved maintenance and standardization. So I'd like to turn this over to David Diaz from Nedick Minster. And David will address some of these topics in his presentation.
Thank you, Pete. Hello, everyone. Pete, would you mind stop sharing? Then I can share mine. Thank you. Okay, let's get to it. Can everybody see my screen? Well,
Yeah, that looks good, David.
okay, thank you. Okay, well, so I decided to start this presentation with a quote, okay, and I am sure most of us have seen certain version of this phrase somewhere else. So to ask the right question is already half the solution to a problem, right? So we're talking today about optimizing stroke rate or production rate without investing a lot of money. Is that the bigger question? Is that what we really want to do? And yes, that's part of what we want to do. But I would say the final goal is to increase our profits, right? From the stamping perspective. So one way to do it is increasing our production rate and using the techniques that Pete already described is one way to do it. But to give one step further, we also need to understand that there are, or we know that there are other costs involved related to produce a part, right? So what's the actual cost of a part? What is it costing us to make it? And I got these concepts from Rob Meyer, also from Minster. He has a presentation on this as well. So the first part in this list is the machine, the investment that we make purchasing the machine and the equipment, and also how do we maintain it. We need to have it well maintained. It doesn't matter if we buy the most expensive press or feed out there if we don't maintain it properly, and it goes to waste very quick. The tooling cost and maintenance, of course, and these days this is becoming very, very important, especially because the tools are getting more expensive, right? With these new materials, there are new coatings, new tool steels, everything is getting more expensive and it's being maintained more often, right? And this is kind of the biggest nightmare, right? The downtime. How do we eliminate or a lot of the cost involved to a part sometimes is the downtime. So how do we minimize it? And there's energy consumed. So pretty much the energy that is being consumed by the part is what it is. However, there are some strategies that we can follow to kind of at least reduce a little bit this energy consumption. Sometimes we forget about the scrap. We just produce the part, we just care about the part, but we forget about the scrap. I believe in the first session, Danny was talking about separating scrap, aluminum especially. So that's part of it. Also, how to design your blanks so that you optimize most of the space or most of the surface on your coil. And obviously, you can optimize your process and other factors. So, how do we start? Well, as I said, we need to use and maintain properly the equipment. And one way to do it is to have periodic maintenance. And especially, as Pete mentioned, it needs to be properly documented. It doesn't matter if we are doing maintenance in a very good way, but we don't have documentation to back it up. Maybe 1 year from today or 2 years from today, we want to remember what happened when we have the press stopped. And maybe the solution, we already know it, but it's not written anywhere, right? So also, especially, for example, if we are checking for clearances on a press, if we do it every 6 weeks or every 6 months or every 1 year, whatever it's your maintenance schedule. If you are checking for clearances and you have properly documented these clearances, and you start seeing that the clearances start to increase, that's normal because of the press usage. But if they all of a sudden they are increasing consistently between every period of time, but all of a sudden between one period and the next period, the clearances changed a lot, then you can detect there's a problem and you can try to fix it before it becomes something bigger, right? So that's the importance of properly document your maintenance procedures. And also good understanding of the press capabilities and limitations, right? Sometimes we think as far as the press goes up and down and it makes parts, we are okay, we are making money, and that's true, we are making money today. But if we are exceeding these capabilities of a press, tomorrow we may have some issues with our equipment. So it's very important that you understand what's the available tonnage curve of a press, what's the available energy curve of a press, what's the off-center loading curve in a press, and many more things, concentrated loads, things like that. Now designing and maintaining the tools according to the process. Again, if you are not selecting the proper coating, if you are having galling issues, if you are not selecting the proper tool steel or the proper hardness in that tool steel, then you are going to stop your press a lot of times and you are going to spend a lot of money during the maintenance. If you don't have the proper cushion systems, especially now with servo presses that everybody likes to run them fast, of course, it's money right there. So on the way up in a servo press motion, we just worry about the coming down sometimes, downstroke motion, and we slow down. A lot of people just slow down during that portion of the stroke. But then on the way up, we don't slow down, we go as fast as possible. And sometimes we damage the cushion, the nitrogen cylinders. So we have to pay attention as well to what type of cylinders do we have. And there are already in the market, I've heard some cushions that can delay the upstroke so that they can have a softer functioning. Okay, and especially we know the cushion or the nitrogen cylinders themselves are not the biggest expense. Again, it's the downtime that they are going to produce is the biggest expense. We need to have balanced loads because I'm showing here an off-center loading graph. If we don't have balanced loads, the press is going to suffer, the tool is going to suffer, the part is going to suffer. So everyone, and obviously proper press speeds. So we talked about what's the impact of having one more stroke per minute, which is a lot. One stroke per minute really is a lot. Now, what's the impact of the opposite? Like, what's the opposite? What's the impact of downtime? Let's assume if you are in the 60-minute die change range. Ideally, it should take you 20, less than 20. Let's say it takes you 60, or some people it even takes them half a day, right? So for now, 60 minutes. And let's say you change 2 times per day. Maybe you change less, maybe you change more, depending on what type of shop you are running. So 2 times a day, 5 days a week, 52 weeks per year. So it's about 30,000 minutes used for die change. If we are producing our parts, being conservative, let's say 15 strokes per minute, it's already almost 500,000 of parts per year. So now you multiply it by the cost of the part and then number of presses when this is happening. Again, it's same thing, just like one more stroke per minute. This is 1 minute that you can use to produce parts, right? It's 60 parts per minute, 15 parts per minute. right? So we need to decrease our downtime a lot. So there are ways to do it. The first one, and without spending a lot of money, the important part. The first part is how do we need to have consistent processes, as consistent as possible. And I know it's difficult. There are a lot of variables that we cannot control. Sometimes we are getting our steel from the same supplier, but still from coil to coil, there are variations. We purchase our lubricant from the same supplier, but the guy who is mixing it or preparing it for its application, he doesn't get the right ratio, or the guy in the night shift, he uses a different ratio, so the lubricant mix is not consistent. Sometimes the tool, where the place where we put the tool in the press is not consistent, therefore the deflections in the press, the tilting in the press is not going to be consistent. So that's something to pay attention to as well, to try to control it as much as possible. Of course, there are going to be, we are not going to be there the whole day to make sure everything is being done right. So there are ways to do it. There are ways to do it there are automated ways to do it, let's say. So for example, we need to also to pay attention to the way we design the tool. When we are designing the tool, we have to, it's most of the time we design it with the process in mind. However, we're deforming the material. We don't want to have fractures. We don't want to have wrinkles. But also we need to pay attention, how are we going to mount the tool inside of the press, or we are going to install it. So in the picture on the left, we see this is the tool, and it has some parallels. Let's say this company had some die lifters. Can they use the die lifters? No, they are being just basically wasted, right? So they can use the forklift to drag the tool on the bolster surface, which by the way is bad, because even you don't notice it the first time you are removing small particles from the bolster, you are starting to scratch the surface. Then the accuracy of the press is going to go down. It's not going to be the same, right? So, but instead, if you are designing your tool, and instead of having just the parallels like this, you have some plates, then you can slide your die on the die lifters, for example. That is going to make the setup process much easier and faster, and less damage to the press or to the bolster surface, right? Also, having these plates, it's going to allow you to put some locators like the ones I showed here, right? Which otherwise you will have to, maybe you will have to weld them here on the parallels. So it's also more difficult to keep the consistency on your tools. Well, those two things I mentioned, I guess they are fairly cheap, or not cheap, but within in the lowest range of expense. But now, as I said, if you do the math and you find out you are, let's call it, you are wasting a lot of money just being lost because of downtime, because of tooling setup, you take so long to do changing tools, why not investing in a quick die change system that you can have moving bolsters, or you can have a cradle to put the next coil before the first one is already being used, or you have hydraulic clampers to install your tools much faster, right? Here we don't need automatic tools because we have the bolster outside. We can do it manually while the press is working. But up on the slide, this is a good option. Now let's see, if you don't want to invest in this type of equipment, still you can have your next coil ready. If it's not sitting on a cradle, at least it can be located very close to the press. You can have the tool ready and very close to the press. You don't need to wait until you are done stamping, until you finish the coil. You don't need to wait until that point to go get the next tool. Okay, so just think about it. Now, I was talking about energy. As I said, the energy consumed by the part, it is what it is. We cannot reduce the energy that is being consumed by the part, but we can manage the energy in the press and the ancillary equipment, right? So this is especially applicable to servo presses, where there are energy management systems that allow us to reduce the size of our transformers, the energy that is going back from the press to the grid, because remember, a servo press can accelerate and decelerate. When it accelerates, it consumes energy. When it decelerates, it generates energy back to the grid. So we can absorb it, we can store it either in a buffer motor or a capacitor bank. We can also improve the efficiency factor or the power factor in our plant. I'm not exactly sure how it works in the US, depending, I guess, on the area. But there are places where having a low efficiency factor is punished. You have to pay a fee, an additional fee to the electricity company for that. So having this type of system is helping you to keep your efficiency or power factor close to 100% or 1. Now, I've seen it plenty of times, how we are happy, we are stamping, we are producing parts, but there's a point where we have to stop the press. Again, and what's the reason for it? We have to stop the press because we need to clean all the scrap that is getting stuck in between inside the press, or we are putting the scrap using shakers, but we have some scrap bins next to the press. We have to stop the press, open, take the bins out, put new ones in there, empty ones. So that takes time. It can be 5 minutes, it can be 10 minutes, but still, if you are producing 15 parts, it's already 150 parts every time you do that, right? You do it 10 times a day, it's already 1,500 parts right there. So using scrap conveyors or other systems to evacuate scrap and to separate it properly, it's very valuable as well. It's an investment. I know that is not without investing a lot of money, but it's worth it. You will recover your money very quick. Now, Pete mentioned about this concept a little bit, and I'm happy he did, because this is kind of I wouldn't say new, but it's debatable. Let's say there are teams on both sides. I'm on the one who is promoting, start looking at distance of bottom and not only at press angles. And it's a bit of a struggle, especially with very experienced people who has been in the industry for so many years, that they are very, very familiar to angles and they want to keep using angles. Remember, with simulation software, you can see the process, you can see when the tools are closing, when the deformation is happening. But in the simulation software, you don't see degrees, right? What you see is distance of bottom, right? Because there's a link, there is a degree to distance of bottom relationship. So for every press, this relationship is going to be different. So the only way to keep it constant or to maintain it as uniform as possible is if we start looking at distances of bottom. If we do that the engineers do that with a computer, for sure, they are going to help a lot during the setup process for different tools. Okay, well, when we are designing the strip layout, it needs to be flexible enough to avoid fractures, right? It's being shown here. This is a picture by Hedrick. But at the same time, it needs to be stiff enough to minimize oscillations most of the time, or not most of the time, but a lot of times, the factor that is slowing us down, the reason why we cannot speed up our presses, it's not because the material is fracturing, it's not because the press cannot do it or the feet cannot do it, it's because the part is just oscillating too much, right? So we need to also pay some attention to the strip layout to make it optimum for high speeds. Now, we can design the motion profiles with the process in mind, especially when we are talking about servo presses. This slide applies only to servo presses. Sorry, this is it should say slow down, pulsating, pendulum, for example. So look at this picture on the left. We have an approach where we are running fast in the through the top of the stroke, and then we are slowing down on both sides when we contact, let's say, the strippers, and when we release those strippers. So it's soft contact, soft release. This is very good approach. However, it reduces a little bit the stroke rate, but still it's better than having everything at 40, for example. Or there's another another approach where we have only half of this of the forming portion at 10 strokes per minute. Obviously, this is going to go faster, but now you are going to be suffering a lot of acceleration here or damage in your equipment. Maybe it's important, maybe it's not. I was 2 weeks ago, I believe, in a plant where they were breaking their die lifters because of the speed. So consequence, they were producing 4 parts per minute more, but if they have to stop the press, they have to change die lifters. It's expense for the lifters, it's expense for downtime, it's everything. So kind of you need to evaluate which approach is best for you if you have a servo press. Now let's talk a little bit about the transfer systems. We talk a lot already about progressive tools. Now, when you are programming a transfer, you have three motions, right? You have the first motion is clamp motion. It's going inside of the press to grab the part. Once we have the part, there's a lift motion. Once we lifted the part to the certain height that we are not going to have any more collisions once we move forward, then we have the pitch or transfer motion. And then we have the opposite motions, right? We just go down, out, and back. So 6 motions, 3 axes. So what do we need to pay attention to when we are programming a transfer? One of the ways to know that you have done pretty much the best you could do with that transfer is that after doing the program, you see all your axes and they are pretty much the same speed everywhere. The number 6, which is the return, typically is higher, so it doesn't really need to be 20 in this example, it can be 50, it doesn't matter. But the first 5 in this example, they need to be pretty much the same. That will tell you that you are not wasting time in any of the axes and that you are using the maximum of the capabilities for each of them, right? If I had, I'm just going to give an example, 40, 40, 40, 40, and 10, this press can only run at 10 strokes per minute. So it was useless for me to program all this at 50 if only, or at 40 if only one of them is it's going at 10. That's going to be my bottleneck, right? So that's one nice approach and very easy to see. Very easy to see if you are optimizing or not your transfer motion. Well, obviously the picture I show you right now, it was a box, square box. We can round corners, right? We can overlap angles. We can start the clamp before the press is fully open. We can start to lift before we already clamp the part. We can start to pitch before we reach the lift height and things like that. I'm going to go a little bit fast so we have time for the questions. This is the same representation, just with it's quiet. It's not moving. Now, very important, very, very important. Make sure your press and your transfer are synchronized, are within the same range of capacity. Sometimes we have a very fast press and not a very fast transfer. So the transfer becomes, also the press speed becomes kind of useless because we are limited to what the transfer can do, and vice versa. Sometimes we have a very fast transfer, but not so much of a press. So that's one way when you're looking at your process to identify whether you can increase your production rate or not. Make sure both of them are pretty much at the same number. One time, one of the customers was working with a transfer and full revolution in a servo press, and he asked me, David, do you recommend a pendulum mode? Should I start looking in pendulum mode? I looked at these numbers and I said, don't waste your time. The press is already going faster than the transfer for this motion. So why do you want to use your time to make it go even faster? You cannot go more than what the transfer can give you, and vice versa. Okay, that's another thing to look for. Now, I'll be quiet for a few seconds. Okay, so I don't know how you guys are seeing it. Hopefully good. If not, please reach out to my email, and I'll david.diaz@nidecpa.com, and I'll share this with you. It's basically when we are trying to move very fast, the transfer, of course, there is inertia in the transfer, and because it's a long bar, there's going to be oscillation, there are going to be vibrations in the transfer, and that's going to create inaccuracies in our process where we may not grab the part properly. and it's going to create faults, right? Slowing down the process. You have to stop the press. We have to fix the grippers. We have to everything. It's just a mess. So with there are simple solutions that are software by software, where we can use anti-vibration modules to mitigate the vibration on the transfer bars. Therefore, we can increase our speed and reduce our downtimes. Well, if we have an integrated system, that is going to save us a lot of setup time. Sometimes the whole system doesn't talk to each other, to each component doesn't talk to each other very well. And if we make a change in the program, we have to go backwards to make the adequate changes to the rest of the program. If we have an integrated system, making a change on the press, for example, is going to send instructions to the rest of the devices to make sure everything is running smooth in a smooth way again. In a very quick manner. I've been involved in the two approaches where we need to make a change on the press and then we need to make a change everywhere else. It's kind of painful and takes time. And I've been in the situations where we just make the change in the press and we just press the button again and everything runs well again. And here I'm showing just another system, but the most important part in this presentation is still missing. And I guess you already know which is the most important part, and that's the human factor. We can have the best of everything, but if we don't have, we need to know what we can do with our human resources. And sometimes the bottleneck is just right there. Okay, thank you very much. I'll stop sharing.
Well, thank you very much, David and Pete, for an excellent presentation. And I think it's fitting, David, that you ended with a shout out to the people. With that in mind, we'd like to bring our expert panel back on, including the metal forming columnists that deliver for metal forming every month. And with Q&A here, we welcome and encourage attendees to submit questions to our expert panel. Please participate by typing your question into the question panel on your browser. Maybe if we can start off with one for Pete right here. Pete, you mentioned that the critical angle changes with press speed. If the critical angle is based on the crank angle when the pilot points enter the die, which is fixed, how could that change with speed?
So the pilot entry angle doesn't change with speed. The pilot, you're right, that's fixed. If it enters at 125 degrees, it enters at 125 degrees. What changes is this is an interactive system. So what changes is the stopping time of the press. So if the press goes faster, it needs more time to stop. So in our example, I think it was like 96 degrees, it stopped at 96 degrees. Maybe it stops at 100. So now, instead of your critical angle being 29 degrees, it's something like 25 degrees. So, and then when you slow down, it's the same thing. So they're interrelated, but I would say the stopping time of the press is more critical. The pilot entry, yes, it's fixed, but it's the stopping time that's going to affect the critical angle.
Okay. And Danny and Danny and Aaron, please feel free to chime in as you'd like. I do have a question here for David. David, when using servo presses, is it always desirable to reduce the speed toward the bottom dead center?
I think the common knowledge would say yes. However, I will look for reverse tonnage. If there is not reverse tonnage, I don't think it's necessary to reduce the speed towards the bottom dead center. However, it's necessary to reduce the speed during contact with the tools. After that, we can just speed up through the bottom and that'll be fine.
I have actually heard of some cases where metals, more exotic metals, would form better as you go to higher speeds. So it's a complex interaction, but there may be some cases which would actually justify forming at higher speeds as you approach bottom dead center. but that's on a case-by-case basis, and most conventional sheet metals would benefit from slowing down.
That's right. Yeah, I've seen, so that's a win-win in that case. It's a production rate increase and formability improvement. And personally, I've seen it with aluminum 6000 series with dual phase and with the Gen 3 980. I'm not sure, Erin, if you have seen it with some other materials, the same behavior.
In those cases, you've got the counter balancing effect of increased friction and increased die wear. So there may be forming benefits, but the process may not be beneficial.
Well, what we have seen recently in many materials, as you speed up the process, at least in the first few hits, you may get a better friction. The reason I'm saying it in the first few hits, because after a while you may get a heating up effect, which takes away all the advantage of that improved friction. So it's a very complicated story. I wouldn't say faster is better or slower is better, but there are certain cases when it's more advantageous to go faster than slower. And in most cases, especially with springs or with breakthrough effects, reverse tonnages, slower would be better, I would say.
Yeah, agree.
Brad, would you like to take any audience questions?
Yeah, thanks, Lou. Yeah, we do have a few questions from our audience. Let me interject those now, if you don't mind, fellas. So the first one we'll go address. This one of our attendees would like a particular, one of the slides that you had in your presentation, David. So this would be a good time to ask Pete and David both. You guys are okay with us sending the PowerPoint presentations saved as PDFs to the attendees, right?
Yep.
Yes.
Yeah, so a good time for me to remind everybody that we will send you guys all the PowerPoint slides that you saw here today. So we got a specific question, maybe for Pete and or David. How often is available tonnage factored into the simulations, figuring that not all of the 300 tons is available, for example, in a 300-ton press when you're 3 inches off stroke press? So how is that factored into the simulations?
Can I jump in here?
Absolutely.
Okay, so first of all, there are these force available curves, but these are most of the time not entered into the simulations. I'm not gonna give any names, but one of these big simulation companies, they also have a press library that you can put in. But to my best knowledge, this information is still not there. So what we suggest is to get all different stations, if this is a multi-station die, all stations cutting on forming forces, put that in a small software that you can find anywhere, and that will give you a few options. Number one is what is the load under each degrees to the bottom dead center. Are you under the available force curve? Sometimes it's called the cutting depth or rated tonnage point. You have to be very careful with that because a 300-ton press might be doing this only on the quarter inch or half inch before the bottom dead center, and that's a huge difference. And most simulation softwares are not taking this into effect directly, so you have to put that in indirectly. And there's also this, what David has also shown us is the off-center loading. Some simulation softwares can handle that a little bit, but I would still advise you to get all the forces from each stations, put them in a separate calculation method, and try to make sure that you have force availability until bottom dead center, off-center loading, and energy, all of them checked.
Yeah,
I don't know if David agrees with me or Pete.
Yeah, I agree, Aaron. It's not just a tonnage problem. You have derated tonnage because you have a mechanical press. So depending on what the angle of the pitman is at the point that you're doing work, you will have derated tonnage. But depending on the distance over which you're going to do that work, that is going to affect the energy consumption in the press. And I'm not talking about electrical energy. I'm talking about the energy that's stored in the flywheel. So especially if you're drawing higher strength materials and or deeper draws, a lot of times your press may have appropriate tonnage, but it won't have enough energy to carry out the work over the distance that it has to be performed.
Exactly, and to add on that, especially nitrogen cylinders or hydraulic cushions, if you apply a lot of Blank-Holder force through a long deep draw, that draws the most energy out of the flywheel.
Right. Just to add to what you already said, Aaron and Pete, we have the simulation and we have the forming forces available from simulation that, as you said, Aaron, we can post-process using another software, maybe Excel, as simple as that. But now we also need to have the information from our press manufacturer, like the available tonnage curve, available energy, and offset loading capacity. In some cases, we're able just to call the manufacturer and ask for those curves. And sometimes, for whatever reason, the press is too old, whatever, and we cannot find it. So I can tell you the energy curve is tough to calculate, I would say. But the tonnage curve, there are some methodologies that you can get a very good approximation within 5 minutes or less. And offset loading, the basic rule of thumb is if your load is centered, you have full tonnage. If your load is under one of the connecting points, it's half of the tonnage. Then you can just put a straight line there, and that's the easiest way to do it. Okay.
Okay, good. Thanks, fellas. Couple questions related to coil bridges specifically. So the attendee writes, we have a coil bridge, but with 7 inches of die travel. So how do you adjust for that so the material is on pass line, but doesn't get bent across the coil bridge when cycling the press? You follow that, Pete?
Yeah, so it sounds like the die has 7 inches of vertical travel, and which is a long distance, and that the coil can bend over the coil bridge.
Yeah, right.
So some of this really needs to be addressed in the design stage. If you know that you're going to have a die that has that much travel, you might want to break up the forming stations to have more forming stations so that you have a shorter distance that you have to travel. Another option is, it makes the die more complicated, is to do your forming so the direction is up. And so you don't have to lift so high off of the lower die steels because all your forming is going up. If the material is thick enough, I don't see that that'd be much of a problem. You might not even need a coil bridge. All processes don't need a coil bridge. I'm just saying for those where you need to support the material, you might consider using a coil bridge. If you use a coil bridge, it doesn't have to expand the entire length of the material. I've seen operations where companies made their own coil bridge, just a single roller, and about half the distance from the feed to the die, they had the material supported, and it was a larger diameter roller. So if it did have to bend over the roll, it was a large radius, so it didn't kink the material. So there are a couple of things to consider there. Unfortunately, die lift, we just lift the part as far as we have to in the die, so we can process the strip, and we don't think about what's happening with the feed system. And that's kind of a disconnect we see in a lot of companies between the design group and the manufacturing group. And a lot of times it's because the design group doesn't get all the information that they need about the press line, or whoever's designing die may not understand the press line and how pilot release works in that, and thinks that the travel is not an issue, but it can be.
Right. So I have a follow-up question for you, Pete. You talked about the importance of adjusting and verifying, if the pass line is exactly parallel, when that lifter is in its highest position. So is that a Is that a complex process? Is it pretty straightforward? Are there best practices that people should follow in verifying that their pass line is actually parallel at the right point, in the lifter height?
So if you establish internally how you're going to define your pass line, in a lot of dies stamped right on the die, the die maker will stamp the pass line because engineering will calculate what the pass line is. But you have to understand what engineering is using. Some companies use the full rails and full up position. Some just simply say, this is the die line, and they call it pass line. Some companies go halfway in between. And so depending on what kind of parts that you're making and the type of material that you're running, some people you can get away with the pass line being halfway in between. So that's the first thing. Understand what the pass line is, and then have that stamped on the die or available at the press. And then the second thing is have a way to measure that. And that's why I showed the one feed unit. I got a photo from Todd Wenzel at TCR Integrated Metal Stamping Solutions. His customer took a scale, epoxied it to the machine, and made a little pointer. And so when they knew that I have to go up 1.5 inches or 25 millimeters, whatever it is, you crank up on the feed till you get that distance increase or decrease on your scale, and you should be very, very close.
Thanks. And then I don't know if anybody wants to comment on recommending where stampers can get a hold of a coil bridge conveyor.
Just Google coil bridge, stamping dies, coil bridge, and you'll find people. A lot of companies make their own. And I just suggest if you make your own, make sure the surface that the material is being supported on is using rollers on bearings. You don't want it to be sliding against a surface that generates friction.
Okay, good.
David, I do have a transfer question. Are there any negative effects to overlapping angles in a transfer? Like how many degrees of overlapping would be acceptable? And should I overlap all the motions?
Okay, three in one.
Good luck.
Yeah.
That's their money's worth.
Well, is there any negative effect to overlap angles in a transfer? If you do it properly, there are not. If you don't do it properly, maybe you start lifting before you fully clamp the part. If the grippers are not adequate, or if you're not using the correct tool, you may not be grabbing the part in the correct way. So that can be one of the issues. Or if you start feeding before you have the proper height, the minimum height to start moving forward, there may be collisions. Obviously, there's software out there that can help you to simulate those things. So those are the only two things that, when you are releasing the part, if you start moving outside before you fully release the part, depending on which system you are using, maybe you may be pulling the part outside of the press, and it's not going to drop vertically on the conveyor, it's going to fall outside of the conveyor. So those are three scenarios that come to my mind right now about negative effects of overlapping angles. How many degrees? Well, if I have to pick, I will start with 5, maybe 5 degrees per angle. That is in overlapping. From there, I will fine tune it after 5 degrees per angle. What was the last part of it? I'm sorry.
Should I overlap all the motions?
Oh, okay, yeah. Well, again, if all of the if you don't have problems picking up the part or putting it in the next station, you can. The only motion where I don't see any advantage is the final one when you are exiting the press. There's people who like it for whatever reason. They like to make that corner as well. They like to start the return trip before they are outside. Up to them. If there's a collision there, you can. That is worth it. That is justified. If there's not a collision, I wouldn't say it's useless, but the effect is very, very minimum. It's just going to create confusion when you start to do the initial home position in your transfer, because the home position is not going to be the corner of that box anymore. It's going to be somewhere else in that curve. So I wouldn't do it there. I wouldn't do it there.
So, would just like to let people know, please use that question panel. We'll stay after a bit, make sure your questions are answered. And David, I do have another one here, bringing a servo press into the equation. You talked about coupling the servo press to transfer motion. What's typically the bottleneck?
Well, I would say in the past, until a few years ago, the transfer was the bottleneck. Transfer systems were much slower than presses, especially than servo presses. These days, transfers are keeping up. They're improving a lot, especially with these modules that I'm talking about, the anti-vibration. They can go much faster. So, surprisingly, recently I've seen human factor being the bottleneck, not the transfer or the press.
Okay.
Automation at the exit of the press is also part of this bottleneck.
Mm-hmm. Okay. And Pete, our press operators are required to do their own setups and run the press to increase efficiency. We like them to be able to set up and run more than one press, but there seems to be an overwhelming number of things that you have to teach an operator to do that. Any suggestion?
Well, yeah, the suggestion that I would have. So what you're experiencing is you need to give more and more responsibility for complex things that are occurring in the press shop. I mean, some of the things I talked about with regard to pilot release timing and feed timing and delays, and some of the things that David talked about in terms of overlap angles. And, you know, now we're going to be looking at slide distances for programming feed lengths and that. Things are getting really, really complicated. And I think very quickly, the era of the press operator is going away. We need metal stamping press technicians. And in my opinion, that needs to be an apprenticeship. There's just way too much complexity. And we haven't even talked about the different materials and problem solving in the press and things like that. Just the complexity of things that have to be dealt with on the press floor. Keep in mind, your press operator is running several $1 million worth of equipment. That should be a highly skilled person. And I think eventually that's what we're going to see. This is going to have to be, they're going to have to be apprenticeships. And the advantage will be that these are highly skilled people that may very well be able to run and set up 2 or 3 press lines and run them effectively. But it's only going to come with detailed training. It's not going to come from, you know, a quick instruction, do this and that. It really needs to be a formalized training.
Would anyone else like to comment on that? Okay. Go ahead.
Yeah, we do another question. So I think this one maybe is for David. So in a servo press specifically, that there's no flywheel. So how do you get the high energy that is required for stamping? Can you talk a little bit about the storage of energy and the use of energy in
in a servo press, you're right, because there's no flywheel to store that energy. All the energy is coming from the grid, and then it's being stored in either flywheel motors or capacitor banks. Just like you can see it just as a battery in your phone, right?
Right.
And then we don't need the grid anymore for that much time. So we still get the energy from the grid, but also we get it from the capacitors. Now the servo motors, when they are accelerating, they are using the energy that is stored in this bank of capacitors, let's say. And when they are decelerating, they are giving back the energy and put it back into the storage system. That's just a back and forth between the capacitors or storage and the press. And of course we have the flow from the grid, but it's not
right.
May I also comment in here for a while? David, correct me if I'm wrong, but in servo presses, I think you should go slower if you need more energy. And in a typical mechanical press, especially I'm talking about with a where frequency inverter slowing down of the flywheel. If you need higher energy, you need to go faster. Am I correct with that, David?
You are saying with a servo press, we need to go slow if we want more energy?
Exactly. Am I correct? Per stroke.
Yes, yes. The production rate needs to be, as you go faster, the energy decreases, the energy available decreases, because then you don't have enough time to put power into the capacitors or the, again, the analogy I make always is the battery of a phone. If you're using your phone or your computer with a demanding operation, you don't have enough time to supply power and the battery is just going to drain. So
Well, maybe you can add more capacitors if you need to speed up. Is it a possibility?
Yes, yes, yes. However, just I want to make the comment that in general, servo presses, regardless of this phenomena, servo presses are going to have much more energy than a conventional press. So even though the energy goes down, and in conventional presses, the energy goes up with speed, that they pretty much they overlap towards the end, let's say. So,
nice to know. Thank you.
Yeah.
So, David, on the subject then of increasing press speed, which we kind of kicked off this whole meeting with that topic. I talked to a stamper a couple of days ago who managed to increase their press speed pretty significantly. By switching to servo and using pendulum mode. And I'm sure you hear this all the time: 50, 60, 70% speed increase sometimes over a conventional mechanical press. But then they were surprised to find out that the tooling was overheating. They were having a host of issues. Can maybe talk a little bit about what to be aware of in your tooling if you're increasing your press speed that dramatically? And I'm sure Pete's got some
yeah. So I will give two concepts, and I think Pete is going to handle them much better. I think you need to pay attention to the coating in your tools and to the lubrication, because temperatures, of course, are going to increase with the increasing speed. So I will look for those two things.
Okay.
Yeah, and at a company I worked with, we had a process that ran relatively quickly. We were doing hole flanging with some ironing. We actually had to cool the tooling. We had chillers with water that would actually flow through the tooling to remove the heat. So, and we needed to remove the heat. It wasn't so much because the tooling is galling and things like that. It was dimensional accuracy that we needed to have. The tolerances were really, really tight. So we had to have a real stable temperature. So even in the morning, we preheated the water to warm up the die and then kept it cool. So it was at a constant temperature. But yeah, the faster you go, the more heat you're going to generate. It's going to change your clearances in your tools. You need good lubrication, good coating. Going hand in hand with coating is you're going to need to select good tool steels that are designed to accept the coating that you would like to use.
If I remember right, there were two articles written in MetalForming magazine by our co-panelist, Aaron. Heat is your enemy and heat is your friend. Thought they were really good summaries of the issues that were just brought up.
Good, thanks, Danny.
But
okay,
on the it was going to change topics. I don't know if there was another comment on heat.
Go ahead, Danny.
But one of the challenges with higher strength steels is increasing deviations from a perfectly flat coil stock. There's additional waviness that just can't be eliminated, or is much more challenging to eliminate. Pete primarily, but maybe David also, do you have any comments? I'm thinking of the pass line comments that you had discussed. How does that change? How does your strategies change if your incoming coil stock isn't perfectly flat?
Well, that becomes more of a straightening issue now. So if you need to correct the shape of the coil coming in, that's going to be done in your straightener. In some applications, depending on, you know, if you're dealing with waviness that's edge wave or center buckle, you may need to use devices such as roller levelers in your plant, or I'm not sure what improvements could be made at the service center by stretch leveling the material. But some of the issues that we have with these very high strength materials, if we introduce work like that, like stretch leveling, and that we remove a little bit of formability. So it's kind of a catch-22.
Right. So what you're saying, though, is that all of the corrective actions have to happen ahead of time prior to stamping. There's no
Yes.
no issues you can correct for if
Well,
the coil's coming in.
You know, a die maker can correct for anything,
This is very true.
right?
Yeah.
But as soon as something changes, that the coil shape is different, now the die maker is back in there correcting again. So really the best approach is that the material coming into the die, any surface correction or edge to edge correction you need to make needs to be done in the feed line and the straightening line. Because if you're going to do it in the die, I'm not saying it can't be done in the die, you'll be forever in the die making changes and making adjustments. So you'd be better suited to do what you can. And that's by one of the things I think a lot of stampers struggle with. If they've worked primarily with HSLA materials and mild steels, they find out very quickly that their straightening equipment for these higher strength steels is not sufficient. It's not sufficient at all. And sometimes they think, well, I got really big rollers in there, you know, that should straighten the material. And believe it or not, you might need a precision straightener with smaller diameter rolls that are backed up so you can work the material harder and get those distortions and shape defects removed.
Right.
And if any changes are made in the die, document. Keep track of it.
And if you can, document back to the coil shape condition.
Absolutely.
Or the blank condition. What did you correct for?
Yep.
Document it so when that problem surfaces again, you know where to go, and somebody isn't figuring it all out from
Incomplete
starting from
records.
ground zero. Right.
Yeah, exactly.
Okay, let me wrap this up, I think, with one more question. I think it's aimed at David. So if you're using a servo press in a transfer operation, and so you shorten the pendulum stroke, but you still need to give the transfer enough time to move the parts. So then you might need to slow the slide down to allow the transfer time to complete the pitch motion. So then you're offsetting the time savings from the pendulum motion. So I guess maybe talk about how you balance optimizing the motion profile in a servo press so that you're not robbing from Peter to pay Paul, if you will.
Right. Yeah, that's a very common thing to do. Here there are two options I would do. The first one is that I would use, some presses have it, what is called decision mode. Pretty much that mode can help you to find what's the best motion profile between full revolution and pendulum from two perspectives. The first one is from the perspective of production rate, which one will run faster. The second one is which one will run with in a more energy efficient way. So that would be my first approach. The second is, because we need to involve the transfer here. The second is I will find out how much transfer time do I need, and then I will introduce that time when designing my process and run again this calculation. I guess there's not a simple answer. You will need to do trial and error. I'm sorry, but
Yeah.
There's no simple answer sometimes, but transfer difficult, not always works with pendulum. It's very tough to work transfer and pendulum. It needs to be very short motions, then you can work with pendulum. But in that size of presses where typically you install transfer, you don't go that fast anyway. So
Yeah.
Good.
Yeah, I would think you would just stick with a traditional press slide motion. You want to go to pendulum motion when you find in your process there are some things that you can optimize. Like, for example, in a progressive die, I feed the material and now I'm waiting for the press to come down. Well, there you might want to run in pendulum motion. But if you've got all this motion in a transfer system, why run in pendulum motion and then stop the press and have it wait? Just have it just continue through a full revolution, and in doing so, you probably provide additional time to restore energy and things like that as well.
Good, thanks. All right, Lou.
Just an outstanding conversation today. Thank you so much, panelists. And to our audience, thank you for attending today's program on press stroke optimization. We hope you found it to be valuable. Once again, an archive of the program will soon be available. When it's ready, you'll receive an email from us. Then you'll be able to review what you learned today and share it with others within your organization. Finally, I want to thank my colleague Brad Coogan and our fine production team for all of their efforts to make our three-part Metal Forming Live event such a success. Our event planner, Ali Miller, marketing manager and director, Drew Gutierrez, art director, Nikki Formica, cameraman, Christian Pokrivka, and last but not least, our producer, Randy Kish. You all did an amazing job. And now we conclude Metal Forming Live, thanking our sponsors and our audience for your support and participation. You may close your browser now. Have a great afternoon.
thank you.
Thanks, everybody.
Thank you. Thanks for having us.